In this lecture, we're going to talk about normal shock waves. It's an important part of compressible flow. It's a very interesting phenomenon. You'll learn in this lecture that shock waves only will occur in supersonic flows. They're non-isentropic processes, and they're pretty dramatic. You get some very interesting changes across a shock wave. Let's go ahead and get straight into it. Take a look at your screen. You'll see a picture here of a person firing a rifle, and you can see some shock waves that form here. First of all, you see the spherical shock wave that's formed. What that is basically, when the person pulls the trigger and the bullet is fired, there's combustion of gunpowder, very sudden pressurized, very powerful chemical reaction with a lot of pressure. And so what you're seeing is the gases coming out of the end of the rifle at very high pressure, and they produce a shock wave that propagates out into the atmosphere. So that this spherical shock wave just gets larger and larger with time. And then you can actually see the bullet here, which is traveling faster than the speed of sound. You can see what's called an oblique shock coming off of it. So it's a very interesting photograph showing these shock waves. And there are many examples of shock waves visualized on the web. So if you do a search on the internet, type into Google shock waves, you'll see some really interesting videos. So let's go ahead and get into the actual material. First of all, just a recap of some of the things that we've covered previously. So we had these relations for adiabatic flow of a perfect gas, for the temperature ratio and speed of sound, and then we also talked about isentropic flow, and so we had isentropic relations for pressure and density. Then we have the area ratio and the choked mass flow rate. So we've covered these things before. I just wanted to remind you of them. When we do the analysis of a shock wave, since a shock wave is non-isentropic, the isentropic relations won't be used, but we can actually use the adiabatic relations, and I'll talk about that in a moment. In fact, let's go ahead and get straight into it. So the way we analyze a normal shock wave, first of all, when I say a normal shock wave, what I mean by that is the flow coming into the shock wave is perpendicular to the shock wave. So this red line here represents a normal shock wave. Shock waves are very thin. So the thickness of a shock wave is on the order of a few microns. So we just treat it as a sudden discontinuity when we model it. It's a very, very thin phenomenon. So we'll just treat it as a discontinuity, and we have flow coming into it at right angles. So that's called a normal shock wave. There are other shock waves where the flow comes in at an angle, so the shock wave might be tilted and the flow comes in at an angle to it. We call those oblique shock waves. You model those in much the same way as the normal shock wave, but we're not going to talk about that in this class. Actually, the way you model that is you just take the normal component to the oblique shock and then use the normal shock relations. But that's outside the scope of our course. We'll just focus on normal shock waves. So what we'll do is we'll put ourselves in the frame of reference of the shock wave, meaning that we're standing on the shock wave and it looks like there's flow coming into it and then flow going out of it. And we'll divide the flow regions into the upstream region, which we'll call region 1, and then the downstream region we'll call region 2. And the way we analyze the shock wave, the relation of the properties from upstream to downstream, is we draw a little control volume that hugs the shock wave. So it's very thin. So part of it is on the upstream side, part of it's on the downstream side, and it's just very, very thin so that all the flow that comes in on the left side only goes out on the right side. You don't have any flow through the top or the bottom. It all just goes from left to right. And then what we do is we apply conservation of mass, linear momentum equation, and the first law to that control volume, and simplify it all down, taking into account the fact that we're dealing with, we use Mach number instead of velocity typically, and we'll assume perfect gas behavior in this analysis. Then there's a separate analysis where we can apply the second law to it, and we'll talk about that in a moment. It should be second law of thermodynamics. I'll just get rid of the of there. And so we can apply the second law as well. I'll talk about that more in a moment. If you go through all of that analysis, you'll get the following set of expressions. They're kind of tedious to derive, and I'm not going to go through that here. If you want to see what it looks like, you can go through my book style notes. It's not critical that you understand the definition. Let me just highlight the things that are important. First of all, we have these expressions that relate the upstream conditions. So here's like the upstream Mach number to the downstream Mach number. Here we have the upstream Mach number, in the upstream pressure to the downstream temperature to the downstream temperature. Here's the one for pressure: upstream Mach number, upstream pressure, downstream pressure. So we have all these relations between the upstream conditions and then the downstream conditions. So if we know what's happening upstream, we can calculate what's happening downstream of the shock wave. One that's easy to remember is what's happening to the stagnation temperature. It remains constant across the shock wave. Now, the reason for that is, let me go back and discuss this, and this starts getting into why we say normal shock waves are non-isentropic processes, is as the flow goes through the shock wave, when we analyze the first law of thermodynamics, you remember that there's this expression on the right-hand side. So the first law looks something like this, and then we have the Q dot into the control volume, right? And then there's a work done on the control volume. So this is the rate of heat transfer in plus the rate of work done on the control volume. Now remember, this is the rate of heat transfer into the control volume. So it would be the heat transfer across these surfaces. Not through the shock wave, but through the control volume surfaces, right? Well, since the flow upstream here, in this whole region 1, it's nominally isentropic, meaning that it's adiabatic and reversible. Recall that we've talked about this in a previous lecture, that those flows upstream, like just flow through through like a channel or something like that, they tend to be adiabatic. There's not a lot of heat transfer because there's not much surface area, or if it's insulated, there's not a lot of heat transfer through those surfaces. And they're modeled as being isentropic because there are no irreversibilities to worry about. And that's true across this surface. There's no real large temperature gradient across that surface. Similarly, downstream, there's no real big temperature gradient across that surface. So there's no temperature gradient driving heat transfer. So we can assume that this is adiabatic. Okay, and then remember, it's the heat transfer across the dotted lines, not through the shock wave. Actually, through the shock wave, there's actually a very large temperature gradient. Okay, and we'll come to that in just a second. But across the dotted lines, there isn't a very large temperature gradient. So the process can be considered adiabatic. And if that's the case, when we go back to our expressions I showed before here, we had this expression for adiabatic flow of a perfect gas. Right? So that's the situation we have here, is we have adiabatic flow through this control volume. So this expression here for temperature is really just our definition for, it's related to the stagnation temperature, right? So what we're saying is that the stagnation temperature will be a constant as we go through the shock wave, because it's adiabatic. It's an adiabatic process. So that's why the stagnation temperature remains constant down here. Okay? So that's an easy one to remember, that the stagnation temperature remains constant. So it's worth remembering. Now let's talk about the isentropic assumption. So it's certainly isentropic conditions, going across the dotted lines here, but through the shock wave itself, there's some I mentioned just a moment ago, there's some large temperature gradients. The temperature from upstream to downstream can change considerably depending on the strength of the shock wave. In fact, the stronger the shock, the larger the temperature difference across it. And since this shock wave is very thin, you get large temperature gradients. Remember, temperature gradient is the change in temperature over change in distance. So the change in distance is very small, and you get large temperature changes. So it becomes a large temperature gradient. You get large amounts of heat transfer that occur across the shock. But and those large temperature gradients drive irreversible processes. So that makes the flow through the shock wave actually irreversible. In addition, you have large velocity gradients. So one of the things we'll show in a moment is that the velocity upstream and the velocity downstream are significantly different. And again, because the shock wave is so thin, you get large velocity gradients. And we know that if you have large velocity gradients, you can have large viscous stresses as well. And so you can have large viscous effects, large thermal effects. Those both lead to because of those irreversibilities. So even though it's adiabatic, it's not reversible, so it's non-isentropic. So you cannot apply the isentropic relations across the shock wave because it's not isentropic. So don't do that. You can do the isentropic relations upstream, and you can do the isentropic relations downstream of the shock, but not across the shock. To connect information across the shock, you have to use these expressions that we derived from conservation of mass, the first law, and the linear momentum equations. Okay, so just keep that in mind, that a shock wave is not isentropic. Now, earlier, a few lectures ago, we talked about sound waves being an isentropic process. Now, a sound wave is a shock wave that's infinitesimally weak. Okay, so just imagine a shock wave, but it's just weak and weaker and weaker and weaker. And what I mean by that is that the properties across the sound wave, if this was a sound wave, the properties from 1 to 2 would be differentially small, just infinitesimally small. In that case, the velocity gradient and temperature gradient across the sound wave would be negligible because it's infinitesimally small, and in that case, the sound wave becomes isentropic because it's the irreversibilities go away because they're just so infinitesimally small, it's not a big deal. So sound waves are isentropic because they're just infinitesimally weak, but shock waves have finite strength across them, and so they are non-isentropic. So let me just talk a little bit. I've been saying that the properties change across a shock wave. I talked a little bit about strong shock waves or weak shock waves. What do I mean by that? So across a shock wave, you can do these calculations on your own, but you get some pretty significant changes across a shock wave. In fact, let me show you. If you plot right down here, what I've done is I've plotted how the properties change across that shock wave as a function of the upstream Mach number. So this is the upstream Mach number. The vertical axis is these things. So let's just focus on the downstream Mach number. So those are these little black diamonds here, I believe. Yeah. Let me highlight that one. So you can see, first of all, that if you have, I've only shown the upstream Mach number is being supersonic. So I'll talk about that in a moment. So just trust me at the moment that shock waves only form for supersonic flows. So that's why I'm only showing supersonic Mach numbers. And then, so this is the upstream Mach number. Let me just kind of remind you, here's our shock wave. This is the upstream side, that's side 1, and side 2 is the downstream side. So the downstream Mach number is all subsonic. So you only get shock waves that form in supersonic flows, and when the flow goes through the shock wave, the downstream flow is subsonic. Okay, so you can see that here. Let's take a look at pressure next. So let me highlight that in green. So the pressure are these little X's. So there's the pressure ratio. This is P2 over P1. Okay, so you can see here that the pressure across the shock wave can increase quite a bit, and it goes up a lot depending on the Mach number. So let's say we have a Mach number of 2 for our shock wave. The pressure ratio is closing in on a value of 5. Let's just, for simplicity, call it 5. So that means that if you had atmospheric pressure here, and then your shock wave is propagating out into atmospheric pressure, if the shock wave's traveling at a Mach number of 2, then the pressure downstream will be about 5 times atmospheric pressure. It's a huge change in pressure. Okay, it's a big change in pressure. And remember, it happens over a distance of just a couple of microns, or a few microns. So it's happening just suddenly. It's like getting hit with a wall of pressure, right? It's a big pressure difference. Those kinds of pressure differences can result in damage to buildings. You can break windows because it's atmospheric pressure and then suddenly 5 times atmospheric pressure hitting the windows. So it'll break windows, it can cause damage to structures, it can burst people's eardrums. Actually, when bombs explode, of course shrapnel kills a lot of people, but the shock wave actually kills people because it's like getting hit with a baseball bat. It's just a huge amount of pressure hitting your body all of a sudden. And you can see that if the Mach number of the shock wave is larger and larger, that pressure difference grows, right? So the more energetic the explosion, the faster the shock wave propagates, and then the larger the pressure difference and the more damage it can do. So when I say a strong shock wave, what I mean by that is a shock wave that's traveling at faster speeds and has a larger pressure difference across it. So you can get these really significant pressure rises across a shock wave, and they can cause considerable damage. Let me just show you what happens to the temperature. So let me highlight that one in a different color. So the temperature are these little squares. So here's the temperature ratio. So you can see that the temperature increases across the shock wave. And let's just go ahead and use a Mach number of 3 as an example here. So here, Mach number of 3, you can see the temperature goes up by a factor of 2.5. So let's say you're standing there, nice, weather, 70-degree day, and then this shock wave comes past at a Mach number of 3. For a brief period of time, the temperature goes up by a factor of 2.5. So it goes up a lot. Okay, and it wouldn't be 70 times 2.5. You have to make it into, you should do it in degrees Rankine, right? So you need to use absolute temperatures, right? So it's either Kelvin or degrees Rankine. It's a significant change in temperature. So that's why if you ever, so you can get a very large increase in the temperature when that shock wave goes by. Now that temperature doesn't stay at that level for extended periods of time. It only goes up for a brief period of time, but that can also cause a lot of damage as well. So let's look at some other quantities. Let's look at the density. That's the R2 over R1. Those are the triangles. So you can see the density of the air goes up quite a bit when the shock wave goes by. So pressure, temperature, density, they all increase across the shock wave. The velocity, those are the black squares. Let me highlight that one in a different color. Let's use gray for that. So the velocity goes down across the shock wave. So it's kind of like the Mach number. The Mach number decreases across the shock wave. The velocity also decreases across the shock wave. The other kind of interesting thing is right now we're doing our analysis in the frame of reference of the shock wave. It's kind of like what we're doing is standing on the shock wave here. It's like we're standing on it and watching the air come in and go past us. But if you put yourself in the frame of reference of the ground, where you're standing on the ground and the shock wave is coming at you, what ends up happening is the velocity up here is 0, but the velocity behind it, so v1 would be 0 in this case, and v2 is actually not 0. So this is another place where a lot of damage occurs because of shock waves. So it's stagnant air, shock wave comes by, and then there's the strong wind that follows the shock wave. It actually follows in the direction of the shock. And that causes a lot of damage to buildings where they fall down. If you ever see videos of like atomic bomb explosions, the first thing you see is a sudden, when the bomb goes off, you see, like if there's a house, you'll see the house smolder initially, and that's because of all the radiation coming off of the atomic bomb explosion. You just get a lot of radiation that raises the temperature and starts to burn things. But then suddenly the shock wave hits, and then everything just blows away, and it's because you get this huge pressure difference that causes damage, and then there's this large wind that follows the shock wave and just blows everything away. Okay, so that's another reason for destruction of very strong shock waves. But you only really see that if you change the frame of reference so that you're standing on the ground rather than standing on the shock. Okay. Now there's some other interesting effects that go on. This one right here is let me highlight this one in a different color. Let's color it blue. The stagnation pressure ratio, those are these triangles. So the stagnation pressure ratio decreases across the shock wave. Now, I've mentioned in a previous lecture, stagnation pressure is related to how much work you can get out of your gas, right? So the idea is we like to have a large stagnation pressure so that we can do something useful with it, right? But you'll see here that if you have a shock wave, that stagnation pressure decreases across the shock wave. So you can't get as much useful work out of the surrounding gas. So this is why when they design aircraft engines and things like that, it's better to isentropically decelerate a flow, to slow the flow down in an isentropic manner so you maintain the stagnation pressure. rather than go through a shock wave. So like when you have flow going into a jet engine, generally you don't want that flow to be at supersonic speeds. Because you can get the possibility of shock waves and things like that that can cause damage to parts in the jet engine. You don't want shock waves. So you really want to slow the flow down to be subsonic. You can slow that flow down isentropically. So if you have a supersonic flow and you decrease the area, that will decrease the Mach number and get you closer and closer to a Mach number of 1, make it subsonic. You could also do it non-isentropically with the normal shock wave. We just talked about this a moment ago, that if you have a supersonic Mach number coming in, if you have a normal shock wave, you'll get a subsonic Mach number coming out. So you could slow the flow down isentropically or non-isentropically. It's better to do it isentropically because then you keep your stagnation pressure where it is. You don't lose any of that ability to do useful work. If you do it non-isentropically, your stagnation pressure goes down. Okay, so anyway, it's one of the factors that go into the design of like jet engines and things like that. And then lastly, we have the sonic area ratio. So when you go across the shock wave, the minimum area required to get to a Mach number of 1 actually goes up. That's this line here with the pluses. So that's another, that actually factors into the design of jet engines, supersonic jet engines, as well as supersonic wind tunnels, but that's outside the scope of our course. So I've tried to summarize these various things just down here. So showing that the temperature increases across the shock and that temperature ratio increases as the Mach number increases and so on and so forth. So I've tried to show all those things here. You don't need to worry about this limit. By the way, I guess I haven't mentioned this before, but that gamma there is just the same as the K. It's the specific heat ratio. Some people use the convention of gamma being the specific heat ratio. Others use K as the specific heat ratio. And so I actually, in a different class, I used to use gamma for the specific heat ratio. So that's why you see that here. But you don't need to worry about that expression. All right, so it's worthwhile for you to know what direction these properties head in across a shock wave. So it's worth knowing that the temperature, density, pressure, they all increase across the shock wave. The Mach number decreases, the stagnation pressure decreases, the sonic area ratio increases across the shock wave. So it's worth remembering those trends. They just help you double check to make sure everything makes sense. Now, I mentioned before that you only get shock waves in supersonic flows. So why is that the case? So if you go back up to our expressions, you'll see here, we have this expression for the downstream Mach number as a function of upstream Mach number. I could easily plug in subsonic Mach numbers here, and what you would get is a supersonic Mach number coming out. So, why can't we do that? Well, it turns out that if you apply the second law of thermodynamics to that control volume, you'll show that it has to be supersonic incoming Mach numbers. So that's what this expression is down here. This is the change in entropy for this process of going through the shock wave for a perfect gas. So you remember this from thermodynamics. If you then plug in our expressions for the temperature ratio across the shock wave and the pressure ratio across the shock wave and plot it out, you'll get a plot that looks like this. So here is the dimensionless change in entropy across the shock wave as a function of the upstream Mach number. And you'll see here that for subsonic Mach numbers down in this range this way, that you get a decrease in the entropy across the shock. Remember, it's an adiabatic process, so there's no heat transfer occurring. You just can't have negative entropy change across the shock. It violates the second law of thermodynamics. So that means you can only have supersonic Mach numbers and shock waves. So that's why we never see shock waves forming in subsonic flows. It would violate the second law of thermodynamics. You only can get shock waves forming in supersonic flows. Okay, so you don't need to worry about doing the analysis for this. I just want you to know why we only see shock waves for supersonic flows. Is because otherwise it would violate the second law of thermodynamics. Now, as far as these equations are concerned, they're kind of lengthy, and kind of a pain to always calculate them. Certainly, if you had access to a computer program or a spreadsheet, you could calculate these things without any trouble. If you're doing it on your calculator, it's kind of tedious. You can do it, but it's tedious. So just like what we did with the isentropic properties, we also put these properties in tables, and they're called the normal shock tables. So I've given you an example of normal shock tables for air. These are in your formula sheet. And what you'll see here is the upstream Mach number given here, and then this will be the corresponding downstream Mach number. So you can see it's supersonic upstream. You get a subsonic downstream Mach number. This is the pressure ratio across the shock. You can see as the Mach number increases, the pressure ratio increases. Here's the stagnation pressure ratio and how that decreases as you go across the shock. Here's the temperature ratio that increases. Here's the density ratio that increases. And I didn't put in here the sonic area ratio. And the reason for that is because the sonic area ratio, let me go back up here, is directly related to the stagnation pressure ratio. You can see that highlighted right there. So it's just, you just flip, if you have the stagnation pressure ratio P02 over P01, you just flip it upside down and you'll get A star 2 over A star 1. Okay, and then that's also related to the stagnation pressure ratio. I'm sorry, stagnation density ratio. So it's just convenient to have these tables here rather than having to do all the calculations. And if you use these tables for calculations, certainly for homework, you should interpolate them to get them more precise. If you're doing a quiz or something like that, you don't have to do any interpolation. You would just use the nearest value because it's kind of a time crunch situation. All right, so I think that's everything I wanted to cover for this topic. Again, don't worry so much about derivations and how, the exact algebra involved in getting these things. All I really want you to know is that it comes from conservation of mass, linear momentum equation, first law applied to control volume. Everything you've done in this class, where we've dealt with control volumes and such, you have all the tools you need to actually do this analysis on your own. I mean, there's nothing new in trying to derive these equations that you haven't seen before. So you should feel pretty good that you've learned these basic tools that can be applied to some pretty advanced problems. But you don't have to worry about the algebra of it. I just wanted you to know where it comes from. All right, so like I said at the beginning, it's kind of neat to see some videos of shock waves in reality and things like that. So I encourage you to do a search on Google to look for normal shock waves or just shock waves. You'll see lots of videos. You'll see some really neat pictures. It's a pretty interesting phenomenon. And it's amazing the power that is associated with these shock waves, just how those large pressure changes and velocity changes can really make a difference to the environment when they pass by. So we'll end the lecture here today. What we'll do in the next lecture is we'll talk about converging diverging nozzles. So in a converging diverging nozzle, as I've talked about in a previous video, we'll have the possibility that in the diverging section the flow can go supersonic. And if that's the case, it's possible that we could get shock waves in those diverging sections. So in addition to analyzing flow through through part of the nozzle using the isentropic relations, there'll be cases where we have to apply the normal shock relations across a shock wave to analyze what all's happening in those converging diverging nozzles. So that'll be in the next lecture. Okay, so we've covered isentropic flow relations, and now we have normal shock relations, and we'll put them all together in the next video.